So welcome back friends. So in the previous lecture we have been saying that Green function methods along with the Feynman-Stuckelberg interpretation of antiparticles will give you the correct results in relativistic quantum mechanics in all the scattering problem, in most of the problems actually, in fact in most of the problems, and that is the right way to go about in calculating scattering problems or any of the issues. Okay. So what we have been starting looking at is how to do derive the Green's, how to define the Green's function methods. This is exactly like in electromagnetic theory, which is relativistic. Of course the electromagnetic theory is the relativistic scenario, classical field theory, whereas we have started with a non-relativistic example like in Schrodinger equation. Okay, this employs all the features of Green's functions methods, and it is quite intuitive. So that is the reason why I wanted to bring it about essentially. So the Green's functions methods are like in time dependent perturbation theory. So what you want to do is again calculate the wave function at a time x and t, x1 x prime and t prime, where the total Green's function is given by this particular function essentially, which tells you that from xt to x prime t prime it goes in this particular fashion. But this Green function is subjected to interactions at specific infinitesimal times at x1 t1 and so on. Essentially, suppose if it is subjected to an infinitesimal interaction at x1 t1 with a potential which is Vu of x1 t1, this is non-relativistic. So that is the reason why I am writing potentials at delta t1, and this gives you a solution in this particular fashion. And then you can write this equation at delta t1 where phi is the solution for the free particle, essentially for the free Schrodinger equation, for the free Schrodinger equation phi, and then you have this particular relation which tells you that delta psi x prime t prime after x1 t1 interaction is given by this particular Green's function essentially. The Green's function now includes a part which is x1 t1, another Green's function between x1 t1 and x prime t prime. So the total Green's function when you sum over all the wave functions essentially can be written in this particular fashion. This is the main equation. The original x prime t prime is the free Green's function without any interactions plus the Green's function which has dot meaning x prime at x1 t1 and infinitesimal interaction localized at x1 essentially. Now there is another important relations of Green's function which is important to mention. Now H contains okay the Schrodinger equation contains, okay, let me write it this particular fashion. The del square operator. So the now the del square operator has eigenvalues equation in this particular fashion. So these are eigenvalues and eigenvectors, eigenfunctions of the del square operators essentially, and they are orthonormal. U's are orthonormal. Okay. Now suppose if one has an inhomogeneous operator, let us just take any differential equation essentially, that let us just take an inhomogeneous operator that is in the presence of interactions and everything essentially. If one has inhomogeneous differential operator so then you have L of ux minus lambda of ux is equal to f of x. F of x ux is nothing but your inhomogeneous part essentially. It has your, it's an okay. This is for any example essentially. L can be any operator, it need not be just differential operator. So let us take this to be an inhomogeneous differential operator on equation essentially. Now L has eigenfunctions which are something like this essentially. So u of x will have some n Cn un of x, and f of x can be expressed in terms of this bunch of eigenfunctions. So the basic idea is we are expanding u of x and f of x in terms of eigenfunctions of L. I will explain in a second what it means. This gives me the relation sigma n Cn lambda n minus lambda un of x is equal to sigma n dn un of x. So this entire relation is given in this particular fashion. Okay. So this means that Cn, this implies Cn is equal to dn by lambda minus lambda. Okay. Okay. Now this implies u of x, the original u of x is equal to sigma n un dot un, okay. Oh no, okay, rather than that this is equivalent to, before that I can write this is equal to f of x is equal to sigma n dn of un of x. This implies dn is equal to un of x into f of x. So this is un of x into f of x un dot f of x by lambda minus n lambda. Now I know this I am going through a lot of calculations, just follow me this through, this is just following me. So what I will end up getting is sum over n un of x lambda minus lambda solid integral un star of x prime f of x prime d cube of x prime so u of x is equal to So, u of x is equal to integral omega g of x x prime f of x prime d cube of x prime. Now, equating these two, you get g of x x prime is equal to sum over u1 of x u1 star of x lambda n minus lambda. So, the sum of all solutions of the differential operator is the Green's function. Now, let me repeat this thing, just bear with me. Okay. What I am trying to say is that suppose, now let us imagine you have a differential operator, L contains some differential operator, essentially L is some differential operator. Okay. L is some differential operator. For example, for Laplacian, let's take it to be u1 of x lambda n u1 of x, something like this. Now, if you have a differential operator in a homogeneous with an inhomogeneous function, this f of x tells you that it is an inhomogeneous function. There is a differential operator u of x, lambda u of x and f of x essentially. This equation has a Green's function solution directly in this particular fashion. U of x is equal to g of x f of x prime del cube of x prime with a surface area with which we have to define with specified boundary conditions and everything, essentially suitable boundary conditions and regions. And surfaces, volumes essentially. So, this you can write it in this particular fashion, essentially this part. Okay. You can write it in this particular fashion, which is g of x f of x prime d cube of x prime. This is nothing but what we had written earlier, essentially. This is in general, this is the same thing, psi of x is equal to this thing. Now, this is the differential equation solution for the Green's function, but what I am doing is take the differential operator and take its eigenfunctions, say if it is just Laplacian, let us say that these eigenfunctions are u of n Cn, and because imagine that I can expand my f of x also in terms of this complete set of bases. If the differential operator has eigensets and eigenvalue, any function can be expressed in terms of complete set of bases. So, I can expand this u of x and f of x into this complete set of bases with different functions Cn and Dn, okay, with different function coefficients Cn and Dn. Okay. Now, put it back into the differential equation, and when you put it back into, this is important that you can expand it in terms of this complete set of bases. So, it forms a complete set of functions. When it forms a complete set of functions, you can always expand it in this particular fashion, essentially. Okay, any function which is consistent with proper things, essentially you can always expand in the complete set of functions. When you expand it in terms of this complete set of functions, so the first assumption is that the differential operator has like a Laplacian has complete eigenvalues and eigenfunctions, and which form a complete set. They are orthonormal set, so they form a complete set. When I can then using this complete set, I can expand this psi. Imagine in our case this u would be psi of x, and f of x would be some v of x, I of x, or something, essentially some inhomogeneous part. So this is in general, because I am not writing for differential equation, for a Schrodinger equation. I am just telling you what happens for the differential operator. I am just expanding in terms of the differential operator eigenfunctions, these functions u of x and f of x, putting it back into the differential equation. I can derive a condition which is un of x essentially. Now un of x, f of x, essentially I can re-express it in terms of un star f of x prime d of x prime over surface, essentially, okay, un of star f of x prime. So I am just taking the mod essentially. Now this is nothing but gives you the relation between the Green's function on u, okay. This tells you what is this Green function. The Green function is un star, meaning it is the sum over all the complete set of wave functions of the differential operator, okay. It is a complete set of wave functions. This is a little mathematical, but this is an important thing, essentially sum of all the solutions of the differential operator is the Green's functions. Now suppose f of x is a delta function. Okay, then using this relation is just u of x will just become the delta Green's function. U of x will just become the Green's function, okay. If f of, suppose then u of x is equal to integral g of x x prime delta of x x 0 d cube of x, that is equal to g of x x 0. So this is L of g x prime x minus L of g x prime x is equal to delta x prime x. So what we found is g is equal to u in the above case with f of x is equal to delta x prime x. The Green's function thus full differential equation with the delta function source. Okay, so what we have seen two properties of the Green's function. This makes our life easier essentially, and these are two important properties of the Green's function. So these are the two important properties of the Green's function. So one is I showed you how the Green's function, okay, these two properties are essentially telling you that one, the Green's function is nothing but the sum of all the solutions of the differential operator, in summing over all the solutions of the differential operator in a given, say, differential equation, say for example all the solutions of the eigenfunction solutions of the differential operator. So we showed it how? We showed it just taking that if these eigenfunctions form a complete set, the eigenfunctions of the Laplacian operator, let us take a Laplacian operator and forms a complete set, and then we write a differential equation. What we can do is, if they form a complete set, every function appearing in the differential equation can be expressed in terms of this complete set of the Laplacian operator, and this will in turn help us express the g of x, okay, the g of x. Now this is you can find this example in I think it is done in Matthews and Walker and Arfken and many textbooks essentially. Mathematical physics, Matthews and Walker, and also you can also find it in Arfken. Okay, when you are reading about Green's functions. So you can show that the Green's function is nothing but sum of all the eigenfunctions of the differential operator. Sum of all the eigenfunctions. This is extremely important. We will use it at various places in momentum space essentially, and that is the reason why I wanted to cover these two topics. Essentially these two topics are important, and these two properties of the Green's function are extremely important. The second important property of the Green's function is that if you put, using this technology, you can using this method, essentially just putting f of x, the homogeneous part, to be the delta function, what you will see is that the wave function itself becomes the Green function. The wave function or the solution of the differential equation is nothing but the Green's function the moment you put f of x is equal to delta of x, because as we have seen the Green's function is nothing but f of x times the Green's function u of x, the solution of the equation is f of x is equal to times g of x essentially. Okay, under suitable boundary conditions and so on, okay, assuming all of that essentially. The Green's function is nothing but f of x times g of x. So the moment f of x just becomes delta of x, the solution of the wave function, the solution of the wave equation just becomes the Green's function. The solution of the wave equation is nothing but the wave equation is the Green's function. Thus we had two important conditions, that the Green's function is the solution of the full differential equation with a delta function source. Okay, this is the important point essentially. This is what we will use to find the Green's function solutions. This is what we will use to find the Green's function solution. So let us start with the non-relativistic case essentially. So this is a simple thing. So we will just use the Schrodinger equation, non-relativistic Schrodinger equation. We will just go through this example very fast, and you can do it as a homework essentially. Let us define the step function theta of tau is equal to limit epsilon tends to 0 minus 1 by 2 pi I integral minus infinity to plus infinity d omega by omega e power minus omega tau plus omega plus I epsilon. So we'll start with the Green's function for the non-relativistic example for Schrodinger equation. So I del by del t prime minus h of x prime g of x prime to x is equal to delta of cube x prime minus x t prime minus t is equal to delta of 4 x prime minus x t prime greater than t. This is forward moving. Now for free particle h0 is equal to minus 1 by 2m delta square okay. So this becomes I del by del t plus 1 by 2m nabla square g0 x prime to x. Now in the momentum space this just becomes d cube p by 2 pi by 4 d omega omega minus p square by 2m g0 of p omega e power minus I omega t prime minus t plus I p dot x dot minus x prime. Okay, let me write it explicitly clear. This is nothing but integral d cube of p. This is a longish expression d omega omega p square by 2m g0 p omega e power minus omega t prime minus t plus I p power x prime minus x. Now why did I this is nothing but your now you see this, why I introduced the step function, because in the momentum space the step function the delta function just becomes a step function essentially. Okay, so this the equation in momentum space in the given in this particular fashion. This so this entire thing is nothing but your delta power 4 x minus x prime. Now given that omega is not equivalent to p square by 2m, this is only possible okay when g of z is 0. This all should be equivalent to delta power 4 given the we have this is your propagator for the non-relativistic fields. So this is the propagator, this is nothing but your Schrodinger equation. Propagator. This is nothing but your Schrodinger equation propagator essentially. How did we derive it? So we put in delta function okay on the right hand side of the Schrodinger equation and started solving it for the Dirac equation okay for the Schrodinger equation, we put a delta function source, converted into, simply re-expressed everything in terms of momentum space. In the momentum space the delta function has everything is given in this particular fashion essentially. So this is what it is, and we use the step function for the delta function essentially, and this gives me the Laplacian and everything we wrote explicitly in terms of the p square, essentially omega is one this, okay, and the g of 0 omega, this is nothing but re-expressing this entire thing. I think there should be a minus sign here. This is fine, this is fine, and that gives me expressing everything in terms of momentum space. H cross omega is your E operator in momentum space, and d omega gives you this. Express everything in terms of momentum space, and now demanding that omega is not equivalent to p square by 2m. We have not done anything, we expressed everything in momentum space. Left hand side we expressed everything in terms right hand side in momentum space, essentially nothing else in momentum space, and now demanding that omega is not equivalent to p square by 2m, we got the condition that g square g of p omega is nothing but 1 by omega square. So this is your first example of a propagator, of a non-relativistic propagator essentially. Okay, I will stop here and then we will continue in the next class. Okay, and now we have successfully derived one particular case for the non-relativistic propagator, and we will do the similar things, exercises for relativistic propagators, and then continue to do so for then use these propagators to calculate various processes essentially. So a simple process like what we said in the S matrix approach. So I will stop here and then we will continue in the next class.